I'm a PhD student at the University of Montreal, working with Professor Marc Feeley. And my work is focused on optimizing dynamic languages for speed, more specifically eliminating dynamic type checks. And as part of my thesis, I've been working on Higgs, which is an experimental optimizing JIT compiler for JavaScript. My current focus has been type specialization, essentially without type analysis in the traditional sense. And in this talk, I'm going to be telling you about basic block versioning and what I call lazy incremental compilation. So my work has been focused on JavaScript. Why JavaScript? Because it's extremely popular right now, and it's also a language with interesting, highly dynamic semantics. So if we just look at a very simple example, this function here, add1, which just returns n plus 1, it has many different behaviors depending on the types of values you feed into it. So if you do add1 of the integer 2, you get back the integer 3. If you do add1 of the string hello, you get back the string hello1. Add1 of true produces the integer 2. Add1 of null produces 1. Add1 of undefined produces not a number. Add1 of an object or the toString methods that returns the string 3 produces the string 31. Add1 of an object or the toString function that returns the integer 3, because toString doesn't actually have to return a string, produces the integer 4, and so on and so on. So you can basically pass values of any type into the plus operator, and you'll get a value back. So basically, every JavaScript operator has some complex machinery hiding behind the scenes, and we want to make this as efficient as possible. So in Higgs, something like the less than operator would be implemented essentially using a runtime function that has all of the logic inside of it. It has multiple type tests, and it implements different behaviors depending on the types of the values that go into less than. Typically, there's going to be a fast path for the case where x and y are integer values. So we test the type of x. If it's integer, then we check if y is an integer, and if they're both integers, we just use some machine instruction that does an efficient less than comparison for integer values. But ideally, to make all of this as efficient as possible, we'd like to eliminate the type checks and just directly inline the machine instruction. And this is where basic block versioning comes in. So basic block versioning is a code generation technique that's similar to trace compilation and procedure cloning, but it works at a lower level of granularity, that of basic blocks. And as we compile code, we accumulate facts. Basically, we use type checks to extract type informations about live variables, and we propagate the information that we've accumulated, and then use this information to specialize basic blocks based on the types of live variables. And we may compile multiple versions of any given basic block. The type tags that we're working with in Higgs are int32, which is a 32-bit integer, float64, which is a double precision floating point value, string, constant, object, which is a plain JavaScript object, array, function. Some of you might note that I put int32 on there, and JavaScript actually has all of the numbers as double precision floating point values, but pretty much every mainstream JavaScript engine tries to use integers when possible to make things perform better, and we've made the same choice in Higgs. So we have a distinction between int32 and float64. So suppose we have a little snippet of code like this where we're checking if some value n is int32. If so, we execute some block B, otherwise we execute some block C, and then we merge into a block D. So as a control flow graph, it looks something like this. Now, if the test evaluates to true, then in block B, we know that n is int32. If it evaluates to false, then in block C, we know that n is not int32. But what do we know in D? Well, we know that n is either int32 or not int32, which doesn't really give us anything. So what we can do basically is tail duplicate D and generate two specialized versions, one where we know that n is int32 coming into D prime, and one where we know that n is not int32. So to generate two versions of block D. In practice, in terms of a little code example, here we have a little loop that performs some bitwise AND operations on some variable V and has some counter variable I. In Higgs, these operators, the less than operator, add, and bitwise AND would be implemented in terms of calls to some runtime primitive functions. The bitwise AND might look something like this, where we have some fast path where we check that x and y are integers, and if so, we use some machine instruction that does the bitwise AND for int32 values. Otherwise, we try to convert x and y to integer values, and then we do the bitwise AND. The add is going to be similar. There's going to be a fast path for the case where x and y are integers, with the slight complication that the add could actually produce an overflow, in which case we're going to want to convert x and y's to doubles and then perform an add on floating point values instead. So now if we inline all of these primitives into our loop body, it looks something like this. So we have 6 type checks, and we have a fast path and a slow path for each operator, for the comparison, for the bitwise AND, and for the loop increment. 2 of these type checks are tautological. We're checking the type of a constant, so we can eliminate them right away. So that leaves us with 4 dynamic type checks that we'd like to eliminate. So what we can do with basic block versioning is we know that I starts with the value 0, which is int32. So we make this supposition that when we enter the loop, I is an int32. And this allows us to eliminate this first type check for the comparison and only use the fast path with no dynamic checking. We can make the same assumption for V, and then we can eliminate both of these type checks by assuming that both I and V are int32 when we enter the loop. So then we can directly use the machine instruction for the bitwise AND. Same thing here for the loop increment. And now we have the convenient thing that bitwise AND given 2 int32 values will always produce an int32. So V remains an int32 for the foreseeable future. There's a slight complication with the add because we could actually have an overflow. So what do we do if we have an overflow? Well, in the rare case where this might happen, we're going to jump to a different version of the loop where we'll make the assumption that I is a double instead. So in that rare case, we would jump into a different code path. But if there is no overflow, we have that I and V remain int32 for future loop iterations. And since this paper has been submitted, we've made a straightforward extension where we can actually exploit the fact that the comparison of I against a limit tells us that I is less than some other int32 value. So then we have that I plus 1 will remain an int32, and we can actually just eliminate the overflow check as well. So we're left with no dynamic type checks in this loop. So what's the difference between basic block versioning and a traditional type analysis? Well, a traditional type analysis would do a fixed point on the types, so try to find types that agree with all possible inputs, which forces us to have a conservative answer that is always valid for all possible inputs. With basic block versioning, we accept that there might be multiple possible solutions of types for different basic blocks, and we don't necessarily have to make a compromise in terms of precision. So basically, instead of doing a fixed point on the types, we're doing a fixed point on the generation of basic block versions. And there are some interesting advantages to this approach. So we can hoist redundant type tests outside of loop bodies. And in some ways, it is more powerful than a traditional type analysis because we can have multiple separately optimized code paths. It can work with some code that's poorly amenable to a traditional analysis, and it can give us answers where it might not be possible using a traditional type analysis. And because there's no iterated fixed point, it can converge potentially faster. So the obvious criticism here is this going to explode? Is there going to be an explosion in the number of block versions? Because if you're generating multiple versions for a given block, you could have a code size explosion. There's one easy way to avoid that. We can simply put a hard limit on the number of versions per block. So this gives us kind of a guaranteed upper bound on the number of versions that we will generate for any given block. And after the limit is reached, we simply try to look for a best match, so to minimize the loss of type information. But we can actually do even better than just putting a hard limit. Possibly we can generate only the versions that are needed at runtime. And this is where lazy basic block versioning comes in. So generating basic block versions eagerly is kind of problematic, because if you want to expand the control flow graph for all possible type combinations, it simply doesn't scale. You get an explosion in number of versions very quickly. You can try to predict which versions for which type combinations are going to be useful, but this is tricky because you need some sophisticated heuristics or maybe some profiling, and you're going to be wrong inevitably in some cases. So you're going to generate versions that are actually irrelevant in practice, that are not needed. So what we do instead is compile block versions lazily when they're first executed. So we compile basic block versions only for the types that are seen at runtime. And we basically let the program's behavior drives the basic block versioning. And we do this by interleaving compilation and execution. With this, we can avoid compiling basic block versions that are not needed. So we can basically guarantee that if you have an integer benchmark, there isn't going to be any floating point code generated. And if you have some code somewhere to handle cases where you have an error that throws exceptions and the exception is never thrown, we're never going to generate that code. So in the example that I gave you earlier, we generated two versions of D, one for int32, one for not int32. This is all fine and dandy when you have only one type text. But you can imagine if you had a cascade of type checks, you could end up with a tree that grows very, very fast in size. But in practice, often what you'll have is that n is either going to be int32 or not, and it's going to stay that way all the time. So if n is always an integer, then we don't actually need to generate the code where it isn't. And we don't actually generate more code, we end up generating less. So basic block versioning is a little bit like eager tracing. We're working with small linear code fragments. One of the differences is that there's no interpreter and there's no recording of traces. So it works by interleaving compilation and execution. And the logic is largely in the branches. So the compiler will keep generating code for as long as it can determine the direction of a branch, so determine which way a type test is going to go at compilation time. And when it doesn't know, it resumes the execution, lets the program decide, so to speak. And when the program jumps to a stub, to a version that hasn't been compiled, compilation will resume. So we're basically writing machine code linearly and patching it. So in terms of an example, suppose we have a function that computes the sum of some integers in the range from 0 to n exclusively. The code generation will actually begin when we call this function first. So suppose we're calling it with some integer 600. We're going to initialize our variables to 0. And then we're going to generate the type test to check is n an integer. And we will actually have two branches that go to two different stubs because we don't actually know if n is an integer or not. So we let the program decide. And in this case, we'll have that n is an integer. So we'll rewrite the jump so it jumps to an out-of-line stub when n is not an integer. So if a future execution has that n is not an integer, it'll trigger the generation of more code. But if n is an integer, we'll just simply fall true to the rest of the machine code. Then for the less than comparison, we do the same thing. We compare our value I to the value n, and then we jump to two stubs. And on the first iteration, I is going to be less than n, so we're going to continue executing the loop body. We patch the jump. Then here we have a sum with an overflow check. Again, we're going to generate two stubs, one for the overflow case, one for the case where there's no overflow. When we resume the execution, in this case, there's not going to be an overflow. So we have the jump to the overflow case is out of line, and so on. The loop increment, we can eliminate the overflow check as I've showed you earlier. And then finally, at the end of the loop body, we have a jump back to the loop header. And now what's interesting is that there are only 7 instructions inside of the loop body, and there are no dynamic type checks inside of the loop body that we've generated. So the machine code is relatively efficient. When eventually the loop condition is no longer met, we're going to jump out of line to a stub that will generate the code to exit the loop body. So I've shown you how basic block versioning can essentially replace all of the dynamic type checks inside of the loop body by one check when we enter the function. Why is this a problem with a traditional type analysis? Well, the issue with traditional type analyses is that we don't know what the type of n is. So if you have an intra-procedural analysis, you don't know what the type of n is when entering the loop, so you don't know for any future iterations either. So for each iteration, you would need to keep checking the type of n. Now, of course, there are ways to handle this, but not with type analysis alone. You would actually need some heuristics and some code transformations. Maybe you could insert a check so that you would guard against the type of n, and then you would perform a type analysis that would take that into account, and you would get a similar result. But then there's also the problem with the overflow. So your loop increment could overflow, your sum addition could overflow, and then you need some additional mechanisms to deal with that if you're using a traditional type analysis. So how does basic block versioning fare in practice? Well, we've tested basic block versioning on 26 benchmarks, and we've tried to answer some questions as to what is the proportion of type checks we can eliminate with basic block versioning, what is the impact on the generated code size, execution time, compilation time, how does basic block versioning compare to a simple intra-procedural type analysis, how does it compare to trace compilation. So this first graph here is the relative number of dynamic type checks executed with basic block versioning compared to a more traditional type analysis. So the white bar is the traditional type analysis, and this is all relative to a version of Higgs which does not use basic block versioning. So 100% would be without basic block versioning. And then we have some bars for basic block versioning with a limit of 1 version per block, a limit of 5 versions, and no limit whatsoever. So what's interesting here is that basic block versioning with 5 versions always does as well or better than the type analysis. And with 5 versions, we obtain something that is very nearly almost as good as with no limits on the number of versions. So we can have a limit of 5 and still get most of the precision. And on almost all of the benchmarks, we get a reduction in the number of type checks executed. This here is bucket counts of the relative occurrence of the number of versions per block. So this graph tells us that in 90% of cases, blocks only have 1 version because we only need because the types flowing into that block are always the same, basically. So we don't need to generate multiple versions per block most of the time. There's a small number of blocks where we generate 2 versions, an even smaller number for 3 versions, and at the end, less than 1% of blocks have 5 versions or more, which is why a limit of 5 versions per block gets us most of the performance. This here is the code size for various block version limits relative to our baseline without basic block versioning. So as we can see, there is one benchmark where we get up to maybe 15% increase in code size, but in most cases, the increase is negligible, and we actually have many benchmarks where basic block versioning will reduce the code size because we're specializing the code and eliminating type checks. So in some cases, we get slightly more compact code. And this is the same graph with eager basic block versioning. So this is just to show you that generating basic block versions eagerly doesn't really work in practice, and laziness makes all the difference. This is the execution time relative to our baseline. So here, less is better. So this shows that in most cases, we have a speed up. In many cases, over 20%. And again, with 5 versions per block, we get almost as good as no limit. This is the impact on compilation time. So basic block versioning doesn't make very much of a difference in terms of compilation time. Again, sometimes the compilation time might be a little bit better because we're generating less machine code. The type analysis that we implemented is not very efficient, so it increases compilation time in every case. Although it might be possible to make a more efficient type analysis. We've been asked to compare our system, our implementation against other JavaScript implementations. So this is a speed up relative to the V8 baseline compiler. I'll note here that the V8 baseline compiler is not crankshaft, so it's not the advanced optimizing compiler inside V8. It's the first line baseline compiler. This compiler has capabilities that are comparable with that of Higgs, so it has a very simple register allocator, and it doesn't do function inlining, just like Higgs. Higgs doesn't have some of the fancy optimizations of crankshaft, like using SIMD instructions and such. So we are able to perform better than the baseline compiler on most benchmarks, sometimes by a few 100%. We've also been asked how basic block versioning compares against trace compilation in terms of performance. So luckily for us, there is a trace compiler for JavaScript in the form of TraceMonkey. So TraceMonkey is no longer part of SunSpider, but back in 2011, it was the state of the art. And again, here, in many cases, we are able to perform better than TraceMonkey, sometimes by a very wide margin. TraceMonkey tends to perform very well on benchmarks that have very small loops, which follow the same execution path every time. So when you have a very tight loop, TraceMonkey can inline everything and get very good performance. But Higgs tends to perform better on the bigger, more complex benchmarks, on the larger benchmarks. And this is a comparison against Truffle.js. So in this case, we have 3 different columns, one with 1 warm-up iteration, 10 iterations of warm-up, and 100. In the case of V8 and TraceMonkey, 10 iterations are sufficient to obtain a warm-up, but Truffle needs more time to reach peak performance. I was told by the Truffle.js people that maybe this comparison isn't entirely fair to Truffle, because possibly it might take closer to 500 or 1,000 iterations for Truffle to reach peak performance. But I think this graph makes an interesting point, which is that Higgs, with basic block versioning, only needs 1 iteration to reach peak performance. And after 1 iteration or 10 iterations, we perform very well compared to Truffle. So future work, there are many interesting directions in which we could expand basic block versioning. I think one of the more obvious ones is that basic block versioning, as introduced in this paper, does not deal with objects. It works with local variable types only. So it has no awareness of object property types. And in JavaScript, global variables are essentially properties of a global object. So basic block versioning, as introduced here, doesn't deal with global variables. So what I'd like to do is to track object shapes as part of basic block versioning and encode property types inside of object shapes, a little bit like it's done in the Truffle object model. And so with this system, the shape of an object would give us property types, and we might be able to generate more efficient code. Another avenue would be to extend basic block versioning interprocedurally, so that we could pass types from caller functions into callees, so essentially have multiple entry points for functions. And possibly this would combine very well with typed object shapes, because typed object shapes can give us the identity of methods that we're calling. So this is it.
Okay. Questions?
So TraceMonkey, when it came out, it did really well in benchmarks, and then eventually it was deprecated as too complex and not worth it on real JavaScript code. What kind of guarantee do you have that this will work really well on real-world code?
Well, I've spoken with some of the Mozilla engineers about this, and I think they said that some of the problems were really software engineering problems. TraceMonkey was rushed really rapidly from being, I believe, a PhD thesis into becoming a production compiler, and there were some code maintenance issues, so that's a big part of the reason why it was removed. I think another issue maybe is that trace compilation seems very elegant on paper, but when you implement it in practice, you run into all kinds of corner cases that are not necessarily easy to deal with. For example, what do you do if you're tracing a loop, and inside your loop you have a function call, and inside the function you have another loop that executes for some number of iterations. How do you deal with that in tracing? Do you do recursive tracing? So there's all kinds of little issues like that. How do you deal with trace explosion? So if you have a loop where you can have a very, very large number of paths that are followed, you need a mechanism to deal with that too. So basic block versioning avoids a lot of these issues by working at a smaller level of granularity. So I think there's some potential there.
More questions?
So this is very cool. Can you say a little bit more about how, so you're not doing inlining in Higgs. So what would the interaction with the inliner be? Does basic block versioning, for example, allow you to do better inlining by inlining particular functions based on the version or something like that?
Yeah, I think that's a definite possibility. That would be very interesting. What I would ideally like to do, maybe as part of future work, would be to have lazy incremental inlining, so that you could inline functions lazily. So essentially, at the level of a given version, maybe you know which function you're calling, and then you could start inlining blocks after some threshold number of executions. You could start inlining blocks inside of your callee, and inline only the code paths that are used at that call site. So I think that would be very interesting work. Fortunately, there's a limit to the amount of things I can do as part of my thesis, but it'd be very interesting to do.
So sorry for a non-technical question, but coming from the University of Edinburgh, where we're very proud to have Peter Higgs on our faculty, I have to ask, why is it called Higgs?
Because it's the successor of a compiler that was named Tachyon. So I tried to stay in the same team.
Okay, I have two questions. With tracing compilers, at least what I've seen so far, we get a pretty big variation in performance across different benchmarks. Sometimes it goes really fast, sometimes pretty slow. What are you seeing in terms of variation with your approach? Is it as wild of a variation as some of the tracing jets, or is it more stable in some sense?
Well, I think that basic block versioning doesn't have as much of an issue. I mean, there's a graph where we compared the performance with TraceMonkey, and as you can see, there are some benchmarks where TraceMonkey does way better than we do, and there are some benchmarks where we do way better than it. And the benchmarks where it does very, very well are the ones that have those really tiny, really predictable loops. But as soon as the benchmarks become more complex, it doesn't do so well. So really, I think the key advantage here that TraceMonkey has over us is inlining. And I think if we had inlining, we could probably beat it across the board.
Okay, then the other question is, I have a vague recollection of something called message splitting from self.
Yes.
And I think it's vaguely similar. So do you know any more details about that?
Yes, I've read the paper. It does something very similar to us, which is it tries to split paths inside of a control flow graph to better propagate type information. From what I've seen, though, the message splitting is particularly directed at loops. And it's actually a very complex strategy. So it's really an interaction of multiple different analyses and iteratively splitting the paths. So it tries to achieve some of the same things, but it's kind of loop-centric, whereas basic block versioning doesn't particularly care about loops. They're just code. And basic block versioning is potentially more efficient.
I don't recall anything about the lazy sort of thing that you do. Is that, do you remember whether they did that or not? Or?
I don't think that they did it lazily itself.
Great, thanks.
Okay, then thanks, Maxime, again.